The question is, if J bar is equal to this expression, right, the current density, J bar is current density, calculate the current passing through a hemispherical shell of radius 20 centimeters and 0 less than theta less than pi by 2 and 0 less than phi less than 2 pi. Okay. So here you have to find out the current. What is the current? This is given by surface integral J bar dot ds bar. So J bar we know in the vector form. We have to find what is the elementary area. So this is already given, the hemispherical shell of radius 20 centimeters, and this is the range. Okay. So the surface that we want, the total surface is a hemisphere. So if you take, this is the z axis and the xy plane, this is the xy plane. So why did we take like this? Because if you can see here, 0 less than theta less than pi by 2. Okay, theta is the angle made from the z axis, right? So this is extending from 0 to pi by 2 and phi is extending from 0 to 2 pi. It's making a complete revolution. Okay. So it will be a hemisphere that is already given, and what will be the radius of the hemisphere? It is 20 centimeter. Okay. So that hemisphere is going to be like this. This is the radius and that is given as 20 centimeter. Okay. It's the hemisphere is lying on the xy plane, the base of the hemisphere. Now since this is a sphere, we will consider the spherical coordinates. So even if you see the J bar current density, it is given in the spherical coordinate system only. Okay. So we can very easily we can use the spherical coordinate system. What will be the area, this ds bar, what will be the vector direction of the surface? See, the vector direction will also always be radial. So it is AR bar. ds bar will always have the direction AR bar. So if you remember, in coordinate systems I have already discussed, whenever you have a surface ds bar whose normal vector is along AR bar, then what will be the other two parameters that we want? D theta and D phi. But theta and D phi, they are not going to come alone, right? How are they going to come? They are going to come along with the radius or whatever it is. For D theta, it is going to be R D theta. Okay. And what about D phi? For D phi, it is going to be R sin theta D phi. This is AR bar. This is how you can write down, very easily you can remember. Okay. So this will become R square sin theta D phi. Okay. Remember, here what we did, first we found out, we identified what is the normal vector to the surface, that is AR bar. So if AR bar is the normal vector, the other two coordinates will form the differential elements. This is the surface, right? So you will have two differential elements. So it will be, those two differential elements will be other than R. So what are the two elements that are left? Theta and phi. But D theta and D phi are not going to come alone. D theta is always accompanied as R D theta and D phi is always written as R sin theta D phi. So this is the final expression that you have for ds bar. Okay. So now you can write I is equal to surface integral J bar is given. What is J bar? 1 by R cube 2 cos theta AR bar plus sin theta A theta bar dot R square sin theta, this is AR bar also, right? R square sin theta D phi AR bar. So if you do the dot product, only this term is going to be there, because A theta dot AR is 0 because they are mutually perpendicular. So what will be the expression that you are going to get? The surface integral, this is surface integral 1 by R cube into 2 cos theta into R square sin theta D phi. Okay. So here theta and phi are the only variables. R is not a variable. R is already given. What is the radius? 20 centimeters. So if you want in the SI units, it will be 0.2 meters. So if you can take out R, you will get 1 by R. Okay. And theta will be varying from 0 to pi by 2, and phi is varying from 0 to 2 pi. Since they are independent, right, they are not depending on each other, theta and phi. So you can integrate them independently. Okay. So what do you have left out here? After you take 1 by r cube and r square common, you have 2 cos theta sin theta. So that is sin 2 theta. So sin 2 theta d theta d phi. So the final expression you are going to get 1 by r is 1 by 0.2 into minus cos 2 theta by 2 from 0 to pi by 2 into phi will be from 0 to 2 pi. Okay, so if you substitute this, you are going to get the final answer 31.4 amperes. Next question. Two extensive homogeneous isotropic dielectrics meet on plane z is equal to 0. For z greater than 0, epsilon r1 is equal to 4, and for z less than 0, epsilon r2 is 3. A uniform electric field E1 bar is given like this. It exists for z greater than or equal to 0. So the question is now to find E2 bar for z less than or equal to 0 and angles E1 bar and E2 bar making with the interface. What is the angles that E1 bar and E2 bar make with the interface? So here this is a boundary problem, right? What is happening? If this is the z is equal to 0 plane is nothing but the xy plane, right? On the xy plane z is equal to 0. So what is happening? You can take the z axis to be like this, the positive z axis, and negative z axis like this. Okay. So now they are saying that the dielectrics meet on this plane z is equal to 0, that is the xy plane. So for z greater than 0, that means the region above this, region above the xy plane. What is the relative permittivity? This is relative permittivity, that is 4. Okay. So here epsilon r1 is equal to 4, and for region less than 0, z less than 0, epsilon r2 is equal to 3. Okay. So this is the boundary. So now E1 bar is given. So we can, this is not required, this z axis. So we can ignore that. Only the xy plane, the boundary we are concerned with. Okay. So here there will be E1 bar and here there will be E2 bar. So E1 bar is given as 5ax bar minus 2ay bar plus 3az bar. Now the first step is to divide this into the tangential and the normal components. So what will be the normal to explain? The unit vector that will be normal to explain is nothing but in the z axis direction, right? So we are taking, what is the direction when we were discussing the boundary conditions? We took E1 to be, the normal direction to be away from the boundary for the first surface, for the first dielectric, right? And tangential component is like this, E1t bar. Okay. And similarly E2 will be like this. So here normal component is going towards the interface. Okay. So this is the E1 bar and E2 bar. Now here we need to find out the normal and the tangential components. So normal component is nothing but perpendicular to xy plane, that is the z component. Okay. So 3az bar is the normal. So we can write E1n bar is equal to 3az bar, and the remaining part is going to be the tangential part. Okay. So E1t bar is equal to 5ax bar minus 2ay bar. Okay. Now from the boundary conditions, we have the tangential components will be same for electric field. So we can write from boundary conditions E12 is equal to ET2 bar. This implies that the tangential component of the second medium is nothing but 5AX bar minus 2AY bar. Okay. So this is the first one. And then, so that is the first bit, right? We have to find E2 bar. So E2T bar we have found out, we just have to find E2N bar. Okay. So what is the second boundary condition? Second boundary condition is D1N bar minus D2N bar is equal to rho S. Okay. So since no rho S is given, we can take this is 0. Okay. So D1N bar is equal to D2N bar. So we don't know the flux density, we have to convert in terms of electric field. Okay. So this is E epsilon R1 E1N bar. This is equal to epsilon R2 E2N bar. Okay. So now we know E1N bar, you know, epsilon R1 you know, epsilon R2 you know. So you can find out E2N bar is equal to epsilon R1 by epsilon R2 into E1N bar. Okay. So this you are going to get 4 by 3 into 3 AZ bar. This is 4 AZ bar. Okay. So now what will be the electric field E2 bar in the second medium? This is E2T bar plus E2N bar. So this is equal to 5AX bar minus 2AY bar plus 4AZ bar. Okay. So this is the first bit answer. You can also write the units. The units are given in kilovolt per meter. Okay. So this is the final answer. Now the second bit, we have to find the angle that this is making. Okay. So if this is the boundary, this is the XY plane, E1, let us say it is making an angle theta 1. Okay. And E2 bar, this is the angle theta 2. Okay, the angle it is making with the horizontal. Now if you take this Z axis, this is the Z axis, right? So the vertical line. So if you take theta 1, you can find it as 90 minus the angle between E1 bar and Z axis, right? And we can easily find out the angle made with the Z axis. How? We can find out E1 bar dot AZ bar, the unit vector along the Z axis. Okay. So what will this be? The magnitude of each of them into the angle. Okay. So this, let's say we will take this alpha 1. Okay. So E1 bar, we know E1 bar and we know AZ bar. So this is 5AX bar minus 2AY bar plus 3AZ bar. This is E1, right? Dot AZ bar. So this will be equal to the magnitude of E1 bar is root over 5 square plus 2 square plus 3 square. Okay. And this will be, so you can just, what will be the magnitude of AZ bar? That is simply 1. So into 1 into cos alpha 1. So you are going to get cos alpha 1 is equal to 3 divided by root over 5 square plus 2 square plus 3 square. Okay. So if you do this, then you are going to get alpha 1 is equal to 60.92 degrees. So our required angle theta 1 is equal to 90 minus alpha 1, which is 29.07 degrees. Okay. Similarly, you can do the same thing with E2 bar. Okay. So you can take E2 bar dot AZ bar is equal to mod E2 mod AZ bar cos alpha 2. So from here also you can find out alpha 2, you're going to get 53.39 degrees. Okay. So theta 2 is equal to 90 minus alpha 2, 36.60 degrees. Okay. So the angle made by E1 is 29.07 and by E2 is 36.60. Here we have a question. Determine capacitance of each of the capacitors shown. Okay, so this is one and this is the second one. Take epsilon R1 is equal to 4, epsilon R2 is equal to 6, D is equal to 5 millimeter and A is equal to 30 centimeter square. So what is D? D is the separation between the two plates and A is the area of the plate. Okay, so we will see the first question. Here if you can see, there is this entire thing is a plate, this is a plate, in between there are two different dielectrics. One has epsilon R1 relative permittivity and the other has epsilon R2 relative permittivity. Okay, so these two you can consider them to be in series. Okay, so in series you first have to find out C1 and C2, and for series connection how will you find out the equivalent capacitance? From this formula. Okay, so first let us find C1 and C2. Okay, so if you consider this epsilon R1 as C1, so here you have the dielectric is epsilon R1 into epsilon naught. Okay, and the area we know it is A, right? Area of the plate is given as 30 centimeter square. And what about the space between them? It is given as D by 2. So C1 is equal to epsilon A by D by 2. Okay, distance is D by 2. So this is equal to epsilon R1 into epsilon naught A D by 2, we can write 2 by D. Okay, and similarly for C2 we can write 2 epsilon R2 epsilon naught A by D. Okay, so now we can find out 1 by C equivalent is equal to 1 by C1 plus 1 by C2. So D by 2 epsilon R1 epsilon naught A plus D by 2 epsilon R2 epsilon naught A. Okay, so you can take out this common factors, you are going to get this expression. Okay, so now what is D? D is given as how much? It is given as 5 millimeter. So you can write this as 5 into 10 to the power minus 3 meter. Epsilon naught is equal to 8.85 into 10 to the power minus 12, and area is given as 30 centimeter square. So this is 30 into 10 to the power minus 4 meter square. Okay, and epsilon R1 this is given as 4 and epsilon R2 is equal to 6. So if you are going to substitute these values here, then you are going to get, this is the value. So from here C equivalent is equal to 1 by 0.00392 into 10 to the power 13. This you are going to get 255.102 into 10 to the power 13. This is the unit of capacitance is farad. Okay, this is minus 13. So if you want to write, you can write in picofarad, which is 10 to the power minus 12, right? So this you can write as 25.51 picofarad. So this is the first bit, right? So if you take this as A and this is B, so this was the first one. Now second one, you can see they are in parallel. Okay, so if you see the capacitance, see these are the plates, this is one plate and this is another plate, but in between these two plates what is happening? Half of it there is one dielectric epsilon R1 relative permittivity and the second half is epsilon R2. Okay, so you can consider this as one capacitor, this as second capacitor and you can see that they are in parallel. Okay, so if they are in parallel, then you have to, when C1 you know, C2 you know, then C equivalent you can find as sum of these capacitances for parallel connection, right. So we have to first find out C1 and C2. So if you take C1 first, okay, we need to find epsilon, area of the plates and the distance between them. So if you see the area, epsilon we know anyways, it is epsilon r1 into epsilon naught, and the area, if you take this entire area, is going to be A, but half of it is covered with, it is given as half, right. So this is given as W by 2 and this is given as W by 2. That means the length, this is the width, right. So this thing is the width and that width is half. That means the area will also be half. Okay. So if the entire area is A, then for this, only this part of capacitor, what is the area? It is going to be A by 2. So here you can write epsilon A by 2 divided by, the separation is going to be D only, right, this entire separation, right. So that is D. So here we can write D. Okay. So epsilon is epsilon r1 epsilon naught A by 2D. Similarly for C2 you are going to get epsilon r2 epsilon naught A by 2D. Okay. So from here you can find out C equivalent is equal to epsilon naught A by 2D, you can take out common, epsilon r1 plus epsilon r2. So you know all the values here, you know epsilon naught A, D as well as the relative permittivities. Okay. So the final answer, you are going to get 26.53 picofarad.